This webcast works some problems related to the universal law of gravitation, and so we'll calculate gravitational force and acceleration due to gravity. I'm in worksheet 7b. The first example involves Hubble Space Telescope. It orbits the Earth at an altitude of 612 kilometers. Okay, so I see the word altitude, and that reminds me that we're talking about, here is the Earth, here is Hubble up here, and so I'm going to be adding the radius of the planet plus the altitude to get the total orbital radius between the center of the Earth and the center of Hubble. Okay, so they give me the mass of Hubble, they give me the mass of the Earth, they tell me the average radius of the Earth, and so we're looking for the gravitational force that the Earth exerts on Hubble. So the orbital radius here, and by that we mean the distance from the center of the Earth to the center of the Hubble telescope, is going to equal the radius of the Earth plus the altitude. And I need to find that all in meters. So the radius of the Earth is 6.38 times 10 to the 6th meters. But notice that they've given me the altitude in kilometers. And so I need to understand that that is 612,000 meters. Okay, so I'm going to add that altitude. And the sum of these things will be the I have misplaced my calculator. Here we go. Will give me the total orbital radius. Okay, so 6.38 e to the 6th plus the 612,000. So that is 6,992,000 meters. Now that I have that orbital radius, I'm ready to find the gravitational force. It's going to be the universal gravitational constant times the large mass, which is the Earth, times the small mass, which is the space telescope, divided by that orbital radius squared. So G is 6.67 e to the negative 11th. The big mass is the mass of the Earth, 5.97. times 10 to the 24th. The Hubble mass is 11,100 kilograms, and then the orbital radius here is the 6,992,000 meters. That has to be squared. Okay, so this is a lot to put in, but we can do this. I have stored the universal gravitational constant in my calculator since we use it so much. And so I get 90,410.798 newtons. That is the gravitational force that the Earth exerts on the Hubble Space Telescope. Let's do another one. Here we have an asteroid orbiting the Sun. The asteroid has a mass of 4 times 10 to the 16th kilograms. And it is experiencing a gravitational force of 3.14 times 10 to the 13th newtons. We have the mass of the Sun. So we want to know how far is the asteroid from the Sun. So here, this involves a gravitational force. And what we are trying to solve for is the distance, which is this r. So I'm going to solve for that r. Okay, so we can bring r out of the denominator, and it's going to equal gmm over the force of gravity, and I'm going to have to take the square root since r is squared. So g times the mass of the Sun is the larger mass. The mass of the asteroid and then the gravitational force that is being experienced is 3.14 e to the 13th. Okay, so we can do this math. And we get that the the distance between this asteroid and the Sun is 4.112 times 10 to the 11th meters. Okay, let's do something that involves acceleration due to gravity. So, many people think astronauts who are at the space station or somewhere are above gravity, that there's no gravity there. Let's see if that's true or not. So we're going to calculate g. Now notice this is lowercase g. They are not asking for the gravitational force. They're asking for the acceleration due to gravity. And so that formula for g is universal gravitational constant times the large mass, that would be the central body mass, divided by the orbital radius squared. Now let's see here. They're telling me how far the space shuttle is above the Earth. And so once again I'm going to have to find an orbital radius here, which is going to be the radius of the Earth plus that altitude. And let's see, the Earth's radius is 6.4 times 10 to the 6th meters, and the altitude is 200 kilometers, so that's 200,000 meters. Make sure you convert that to meters. And we get 6,600,000 meters. Okay, so over here, when we're calculating lowercase g, the acceleration due to gravity, it's going to be the universal gravitational constant times the mass of the Earth, the big mass, which is 6 times 10 to the 24th kilograms. The orbital radius is that 6,600,000, and that orbital radius has to be squared. And so we get 9.187 meters per second squared. So it's not zero at all. In fact, you may be surprised at how big a percentage it is of the acceleration due to gravity near the surface of the Earth, which is 9.8. Question B says, what percentage is your answer of that acceleration due to gravity? So I'm going to take what we found on orbit, 9.187, and divide by the acceleration on the surface of the Earth, and we're just going to find this as a percentage. And we actually get that it is 93.75%. So you're certainly not at zero gravity when you're on the space shuttle or in the space station. Okay, let's look at problem 4, where we have a space probe in a circular orbit around Mars, and it's a distance of 300 kilometers from the surface of the planet. Okay, so once again, we're going to need to find that orbital radius. In this case, it's going to be the radius of Mars plus the altitude. And so it's going to be, let's see, oh yeah, so look at this, 3.39 megameters. So I need to understand what mega means. That's 3.39 e to the 6th meters, plus 300 kilometers is 300,000 meters. So the orbital radius is 3,690,000 meters. Okay, so the first question is the acceleration due to gravity. So again, I'm noticing this is acceleration due to gravity. That is lowercase g. That is not the force of gravity. And I want to use the correct formula for that, which is universal gravitational constant times the big mass, the central body mass, divided by that orbital radius squared. So be careful which mass you use. Acceleration due to gravity is determined by the celestial object, which in this case is the planet Mars. And so I want to use its mass, which is 6.39 times 10 to the 23rd kilograms. Acceleration due to gravity is not determined by that little space probe. Okay, the orbital radius at the location of the space probe is that number we just found, 3,690,000 meters, and that r has to be squared. Okay, so the acceleration due to gravity at that location is 3.130 meters per second squared. Then the question is, what is the acceleration due to gravity at the surface of Mars? So this is the g on orbit, you know, where the space probe is. But what about on the surface of Mars, the acceleration due to gravity at Mars? So it's the same formula, but we're going to use a different r, right? Now, the r, the orbital radius, is not the radius that includes the altitude. It's just the radius of Mars. So it's going to be g times the mass of Mars divided by the radius of Mars, which is 3.39 e to the 6th, and that has to be squared. Okay. And so we get 3.709 meters per second squared. Okay, so it's bigger on the surface of the Mars because you're closer to the center of that planet. And you know, g gets smaller as you move away from the planet. Okay, on C it says, how much does the space probe weigh in its orbit above Mars? So the weight of the space probe equals the mass of the probe times the acceleration due to gravity in orbit. Okay, I need to use the g at the location where I want to know the weight. Now the mass of the probe is 439 kilograms. You know, that's the same everywhere, the mass. But at its location in orbit, the g is 3.130. And so I get a weight of 1374.2 newtons. And what if the space probe were to land on Mars? Then it would be on the surface of Mars, so its weight on the surface would be the mass times the g on the surface of Mars. So it's the same mass, but the g there is 3.709. And so it's going to weigh a little bit more. It's going to have a weight of 1,628.1 newtons.